We continue our notes on electric circuits, and we finished up the last one talking about resistors and the color code of resistors and a basic battery and which way the current flows in there and characteristics of batteries and what that means. We discussed resistivity, the difference between resistivity and resistance, did an example problem with both information about resistance and resistivity. And you were to have done and turned in already graded homework problem 3, 7, and 9. Let's continue. I think we'll be able to finish this chapter today. We're going to talk about electric power, which is the last major concept in here. And basically, electrical energy can be transferred into other forms of energy, like we've already seen. Examples are things like heat, excuse me, mechanical energy like electric motor, like a light bulb, and sound energy like a speaker. And heat can be anything like a light bulb or electric heater that you might have in your house already, like a portable electric heater. Most electrical devices are rated by watts. When you go and purchase a light bulb, you get like a 50-watt light bulb or a 75-watt light bulb or a 100-watt light bulb. Watts are units of power. We've had this before. And the unit watts are a measure of the amount of energy per unit of time. We're going to go through some derivations here for some equations. We're going to probably have a new equation or so that's in there, but we'll try and explain that whenever we get to a new equation. And talk about power and how it's derived. Again, power is the amount of energy per unit of time. Now, energy in electric circuit, the energy of charge moving through a potential difference remember, potential difference is the same thing as voltage, is determined by this equation. Work and energy are the same thing, is equal to the amount of charge Q passing through a potential difference V. This is, I think, a new equation, but we're going to use that to help us identify power in terms of voltage, current, and resistance. So this power is equal to the energy. Remember, work and energy are the same thing. So we're going to take this equation. This is going to be work over time, but we're going to use work in terms of QV over time. So this is a power equation, QV over T. Now remember, we know that current is equal to charge over time. So this quantity right here, Q over T, is the same thing as current. So we can write power equals current times voltage. This is one form of a power equation. There are actually a couple other forms of power equation. We're going to derive those right now. So we also have the fact that Ohm's law is V equals IR. What I'm going to do, I'm going to substitute in this equation for voltage, IR. So this is the power equation. Power equals I times V. I substitute in for V, I times R. We can combine those currents. We get power equals I squared R. This is another power equation that we can use. And there is a third one. I'm going to rearrange Ohm's law in terms of current. So V over R is equal to current. And again, I have power equals I times V. What I'm going to do is substitute current into this equation in terms of V over R. So power is equal to V over R times voltage. We combine that, we got power is equal to V squared over R. It's another power equation. So there are three power equations that you can use. Which one you use just depends on what information you're given in the problem. Let's take a look at units of power. Again, power is work over time. Those units are joules per second. We call 1 watt the same as 1 W. W is a unit for watt, and 1 watt is 1 joule per second. Now, I'm going to take this equation, write in this form. Power times time is equal to watt. Now let's take a look. 1 kilowatt hour is something that we're used to saying in terms of kilowatt hours. 1 kilowatt is the same thing as 1,000 watts. 1 hour is the same thing as 3,600 seconds. 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules, because a watt is a joule per second, so these seconds cancel out, and that's joule. So a kilowatt hour are energy units, not time or anything else. Let's see how we can use some of this information to solve a problem. We have an electric heater, draws 15 amps, so the current is 15.0 amps. The voltage is 120 volts. We want to know the power it costs per month, 30 days per month. So the time that we have here is 30 days, but it operates for 3 hours per day. And the cost that the electric company charges, this is 9.2 cents, which is $0.092. Okay? So this cost is $0.092 per day. So we can get the power is equal to current times voltage, because we know the current and voltage. So this power is 15.0 amps times a voltage of 120 volts. That power is 1,800 watts. Now, we can convert this to kilowatts. 1 kilowatt per 1,000 watts. That's going to give us 1.80 kilowatts. I'm sorry, this is 0.092 cents per kilowatt hour. Sorry for that. So now, we're going to take this 30 days and 3 hours, count how many hours per month that actually is. So this is 30 days per month. It's 3 hours per day. So it's actually 90 hours per month that this is operating. Then we take our 1.80 kilowatts, sorry, and use our 0.092 cents per kilowatt hour, $0.092 per kilowatt hour. Kilowatts cancel. Then we have hours. This is 90 hours per month. Months cancel. Then we have our cost per month, and that's what we're trying to solve for. And that's going to be approximately $15 per month. Let's take a look at another example problem. Let's calculate the resistance of a 40-watt automobile headlight designed for 12 volts. The information we have, power is equal to 40 watts. Voltage is 12 volts. And we want the resistance. Let's take a look. Since we have power and voltage, we can use power equals V squared over R. Put in this information, 12 volts squared over the we know the power, 40 watts. 12 volts squared over the resistance. We're solving for this resistance. We end up getting 3.6 ohms for that resistance. All right, let's take a look at one more problem. Lightning is a spectacular example of electrical energy. A typical lightning bolt can transfer 1 times 10 to the 9th joules of energy. Joules is energy or units of work. 1 times 10 to the 9th joules. Voltage is 5 times 10 to the 7th volts. And the time is 0.2 seconds. And we want to know the amount of charge. Well, we know that work is equal to QV for charge moving through potential difference. We used that in the derivation in the previous problem. So the amount of energy that we have, or work, is 1 times 10 to the 9th joules times Q, and the voltage is 5 times 10 to the 7th volts. We get that amount of charge to be 20 coulombs. What's the current in the lightning bolt? So we're solving for current. The equation for current is charge over time. We have the charge and we have the time. This is going to be 20 coulombs divided by 0.20 seconds. We get that current to be 100 amps. What's the average power? We have both current now and voltage, so we can have the power equation of current times voltage, which is 100 amps times a voltage of 5 times 10 to the 7 volts. We get that power to be 5 times 10 to the 9 watts. We convert that to gigawatts. 1 gigawatt is 1 times 10 to the 9 watts. Then that is what we call 5 gigawatts. Large amount of power. I think power in household circuits. I know a lot of you have circuit breakers or fuses in your house, and sometimes circuit breakers and fuses in the electronics of the car. And the equation, power equals I squared R, is a common equation to determine the power used to produce in a circuit. If current is too high, the circuit will heat up and pose a fire hazard. So what households have are fuses or circuit breakers that stop that from happening. Let's take a look at a little household circuit that can show you how this works. I'll have this filled in already to save some time. This is what we have. All of the household circuits run on 120 volts. Depending on the apparatus that you have, will determine the energy that apparatus uses. Like a light bulb is 100 watts, like a heater is 1800 watts, a stereo receiver is about 350 watts, and a hair dryer about 1200 watts. All of these are connected to a power source that provides 120 volts to each of those devices. So the voltage across each device is 120 volts. It says the fuse, this is a circuit breaker or the fuse, can only withstand 20 amps. If it gets larger than that, the fuse will burn out or the breaker will switch off. So what we do, I'm going to call this current going through the light bulb I1, this current I2, this current I3, and this current I4. We know the power, the wattage, and we know the voltage, 120 volts. So for each of these, we can determine the current. This is the current going through I1, the same thing for I2, same thing for I3, same thing for I4. We add all those currents up, that's a total current going through that fuse. If that current is greater than 20 amps, we add all those up and there's 28.8 amps. This is greater than 20 amps, so the fuse is going to break. And that's it for chapter 18. Check LMS for other assignments.